Welcome viewers to the 17th lecture in the open online course Computer Numerical Control of Machine Tools and Processes. So, in today's lecture we will be covering certain aspects of curved surface geometry. So, to start with, there are different types of parametric surfaces which are employed for representing shapes in connection with modeling and machining, and among these the non-uniform rational B-splines or NURBS surfaces are used to represent all surfaces and curves of CAD models, because they can represent all sorts of geometries. However, in today's discussion we will be restricting our discussion mainly to Bezier surfaces, because first of all Bezier surfaces are easier for sharing concepts, not as difficult and complex as non-uniform rational B-splines, and still the basic mathematical form of Bezier surfaces, B-splines, non-uniform rational B-splines, basic mathematical form is the same. So, Bezier splines, B-splines, cubic splines, NURBS, etc., they all belong to the family of spline curves. So, let us have a quick look. This we have already seen once, but let us have a quick look. That is, the Bezier curve first of all is being represented here, and there are 4 control points B0, B1, B2, B3, which are basically controlling the shape of this particular curve. In what way? They are having multipliers as shown there as a summation. The curve is being expressed as a summation of the control point coordinates, that means B1, B2, B0, B1, B2, etc., multiplied by a weight function. This weight function is called Bernstein polynomial, and the expression, the way in which Bernstein polynomial is calculated, it is given at the bottom. That means, basically it is NCI u to the power I 1 minus u n minus to the power n minus I. Okay. And what is u? U is a parameter which takes up values between 0 and 1 proportionate to the position that it has with respect to the beginning point and end point. If we measure the length along the curve up till the point under consideration, then the fraction of the length of the curve divided by the total length of the curve gives us the value of u. So, in this way I is the particular term under consideration starting from 0 ending up in n, where n is 1 less than the total number of control points, and Bernstein polynomial is calculated this way and multiplied with the control point coordinates. So, if the control point coordinates be x, y and z, that means, if it is a 3-dimensional curve, in that case with each of these coordinate values this Bernstein polynomial will be multiplied, and it will be contributing to the x, y or z value of the particular coordinate point being calculated this way on the curve. So, this is a point on the curve coming out after calculation in x, y and z, B I control point coordinates being given as x, y and z, and the Bernstein polynomial being calculated with as a function of the parameter u and dependent upon the total number of control points. Well, Bezier curves and surfaces can be represented in different ways. This is the summation form, this is the polynomial form. That means, after working out all those Bernstein polynomial expressions, it can also be represented this way. If you remember u to the power I into 1 minus u n minus I, etc., those things are appearing here, 1 minus u to the power 3 and 1 minus u to the power 2 into u, like that. So, this is the polynomial form. It can also be expressed in a matrix form, where this particular u matrix, capital U matrix, will be containing terms only as functions of u. the intermediate x matrix called the coefficient matrix, that will be containing some constants depending upon the number of control points that we are considering, and the B matrix will be containing the control points that we are considering. In this case, if there are 4 control points, they are put as a column for this particular Bezier curve expression. So, as a product of matrices, it looks finally like this: U matrix, coefficient matrix, and the control point matrix. I am sorry, the other side of the subscript, I mean the bracket has somehow got obliterated, it is very much there. So, if we similarly if we look at the equation of the formula of the Bezier surface, it looks this way. The Bezier surface has this u parameter varying from 0 along the edge up till this point where it takes up a value of 1. Here also, along all these lines moving from this side to that side, the u value takes up a value of 0 at the start and moves along, increases its value and ultimately reaches a value of 1 here. So, at intermediate positions also there are lines which are called isoparametric lines, along which the other parameter which is mentioned here as w, that will remain constant and u can be increased so as to produce a curve right from this side to that side, u varying, but w remaining constant, and that line being known as an isoparametric line. So, if we express the expression of the Bezier surface as a product of matrices, it will appear as just as before: the u matrix, the coefficient matrix for the u side, the control point matrix, the coefficient matrix for the w side, transpose, and the w matrix, that means the other parameter w, transpose. So, u matrix coming out as, so it is clear from this expression that if we are looking for terms containing u or its higher powers, it will only be present here in this matrix. So, we have successfully segregated all the terms in different matrices, w only here, control points only here, like that. So, when we come to these two, u and w, they are containing only u terms or only w terms, and this is containing only the control point coordinate terms. So, if we express the surface, I mean if we try to draw the surface, this is the Cartesian space representation of the surface. If we draw the surface on a UV plane, that means just like a graph paper where x is replaced by u and w replaces y coordinate, in that case the surface will look exactly like a rectangle, or rather a square in this case, because both sides of the rectangle, I mean adjacent sides of the rectangle, they are equal. So, if that be so, this is the surface and it stretches from 0 to 1 on this side and stretches from 0 to 1 on that side. So, this is exactly what the surface looks like, and interestingly the isoparametric lines will come straight parallel lines to the x or the y axis, as the case may be. So, we will have grid lines x parallel to y parallel to x appearing here, which will be the isoparametric lines. Coming to data fitting, what do we mean by data fitting? Data fitting means that control points may be controlling the surface, but designers might be interested to have a curve which initially passes through a number of points. Let us have a look at this particular case. Suppose there is a designer who has designed a very nice looking car body, and he asks the person who is handling the geometrical aspects of the design, pass a curve through these points. So, these are now not the control points, but points through which the curve has to essentially pass, and therefore, after a successful drawing of the curve, the Bezier curve could look like this. It should have positional continuity, that means it should pass through all these positions, and it should have directional continuity, that means commonness of the slopes and curvature continuity through all these points. So, if we have a Bezier curve of this type which passes through all the points, these cannot essentially be the control points. Control points are points which are controlling the surface, but they are not the points through which necessarily the surface has to, or the curve has to pass. So, these we are calling as data points. Okay. So, these we are calling as data points. If these are the data points, then how do we handle, how do we obtain the curve and its control points? If we do not get the control points, we do not have the curve. So, let us have a quick look how this is done. Coming back here, so these points which we have drawn on the curve, these are the data points. It is provided to us, and I have to find out the control points which are not known to me. Of course, the first and the last points, data points, are also the control points, because in case of Bezier curves, the last and the first point, they are shared between data and control points. So, we are faced with a problem in which I have to find out the control points, and I am simply given a number of data points through which the curve is supposed to pass. So, in that case, we can frame a matrix representation of the conditions this way, that these are the data points in x, y and z. So, each what do you call it, letter here d1, d2 etcetera, they represent x1, y1, z1 or x2, y2, z2, like that. And each of these terms, they are the Bernstein polynomials corresponding to a particular value of the parameter. That means, the parameter value corresponding to this point is given in the second line. Okay, u2 corresponds to the parameter value here. Now, the problem is, if I do not have the curve, if I cannot measure the length along the curve, then how can I possibly assign a particular parameter value to this point? The solution to this is that we can make an approximation in which the chord lengths can replace the arc lengths. Instead of taking arc lengths, that means length along the curve, we will take the chord lengths this way and approximate the value of u1, u2, u3, like that. This is called chord length approximation. So far so good. Therefore, I can have numbers against all these terms. This part of the problem is solved. What about this particular matrix? None of these points are known. These are actually the unknowns which have to be solved. So, I do not know this particular matrix. I do know these points. Yes, I know these values as numbers, because I have been able to assign certain values against u1, u2, u3, u4 by approximating the arc lengths by the chord lengths, and that way I have been able to find out some parameter values corresponding to these points. Do I know these points? Yes, these are given. These are the points which the design engineer has given to me, and he wants the control points, or rather he wants me to draw the curve after getting the control points. So, in this case, if there are 4 data points, I will have 4 such rows, that means 4 equations can be formed, and from that definitely I can solve for 4 unknowns. Therefore, if the number of points and the number of control point, number of data points and the number of control points, if they match, I do not have a problem. I can exactly solve this problem and I can get these points. The problem occurs when there are more number of data points than the control points. Why so? This is because, say for a particular curve which is belonging to part of the whole of the car body, there will be so many number of points which the design engineer would be providing me. So, as a simple approximation, simple representation of the problem, let us say how many points are here? 1, 2, 3, 4, 5, 6, 7. 7 points are here, and 1, 2, 3, 4 control points are here. If I take 7 control points, my problem is solved. I can have an exact solution and the curve will exactly pass through all these points. But if I have 4 points, then the curve can only be solved in a mean sense, or a least square fit, you can say, and averaging, or what do you call it, the sum of the square of errors will be the least, but it won't pass necessarily through all the points. Now, the question is, why should I go in this direction, which is obviously creating a problem for me? Why not make the number of points, control points, equal to the number of data points? The problem is, if there are huge number of control points, I have the highest power of the polynomial in the Bezier curve to be equal to number of points minus 1. If you have 4 points, you get a cubic Bezier curve, that is the highest power is the u to the power 3. If you have 100 points, 100 data points, and you solve for 100 control points, you will get u to the power 99. Now, just imagine u to the power 99, and the computer has to crunch all these numbers again and again through different calculations, tangents, normals, this, that, etc. And you are going to just lose time for just a just a whim of yours that you have to have equal number of control points and data points. So, we have to go for this approximation. That particular requirement for accuracy just cannot be taken care of with Bezier curves and surfaces. So, what we do is we solve for it in this manner, in this manner, that is, we multiply the transpose of the Gaussian matrix on both sides. After that, it can be inverted, and after that we get the solution of the control points as the least square fit. Okay. So, this is about curve fitting with Bezier curves. Now, therefore, what do we arrive at? We understand that the highest power of the Bezier parametric equation is n minus 1, where n is the total number of points, and if number of control points is high, we have a problem. The degree of the Bezier polynomial is also high. If one control point on the Bezier surface is changed, this is very important, it affects the whole shape of the whole curve. Therefore, effects cannot be localized. Is this a problem in case of B-splines or non-uniform rational B-splines? No. In case of B-splines, rational B-splines, etc., we have yet another curve modifying parameter, which is called the knot vector. The knot vector comes in and it essentially divides the curve into different segments, and these segments can be individually controlled. So, this problem of the Bezier surface, that is change of the location of one point affects the surface globally, that is not a problem in case of a higher more advanced curves of this family. And if we have data fitting, which we discussed just now, a perfect fit is not possible if you want to go for less number of control points in connection with more number of data points. However, one thing is good, that is, once you have made the matrix inversion and obtained the control points, then if you want to make some aesthetic changes, etc., say to the car body, then you can simply change the locations of the control points. Matrix inversion at that stage is not required. So, let us now have a look at tangents, definitions of tangents, normals, etc., with respect to the Bezier surface. So, what do we have here? We have the Bezier surface where one side is having the parameter u associated with it, the other side is having the parameter w associated with it. instead of x and y. That means, the basic formula that we observed for this curves, surfaces, etc., they are having the variable not in x, y and z, but in the form of parameters u, w, etc., because of which they are referred to as parametric surface equations. Now, coming to the inside of the surface, what does this orange line represent, orange curve? The orange curve represents a line along which the parameter w is a constant. So, we call it the isoparametric curve. Okay. Along this, w is going to remain constant and u is going to constantly increase from 0 up to 1 here. It is easy to find out the points on an isoparametric line, because we can simply, in a do loop or a repeat loop inside a program, go on incrementing the value of u and go on finding out the x, y, z points on the surface, and that will give us the isoparametric line. In the same manner, you can also have an isoparametric line, I mean curve, in the other direction where u is made a constant. So, if u is constant, you will get the isoparametric curve in this direction, starting from 0 here and ending up in 1 at this point. If we derive the expression of a Bezier curve, it is a function of two parameters u and w. If we derive it partially with respect to u, we will get a derivative which will come out as a vector as shown here. This one is the partial of the surface with respect to u, and we are assigning a symbol r superscript u to represent the derivative of the surface with respect to u. It is a partial derivative. In the same manner, if we derive the expression of the surface with respect to w, we are getting this particular derivative, and in space it will look like this one. So, these are essentially two tangents to the surface. The surface has infinite number of tangents in a plane called the tangent plane, touching this particular point on the surface, and it has one normal, infinite number of tangents, one particular normal, and if we take the cross product of r u with r v, then we will get this particular normal. Okay. Now, let us have a quick look about the way in which we are supposed to find out these tangents and normals. For example, the surface expression is written at the top, and it is expanded once to show how the U matrix looks like. So, the U matrix contains 1 U, U square, U cube, etc. If we now derive it with respect to U, the beauty of it will be only one matrix will be affected, only the U matrix. So, we do not really have to concern ourselves with complex mathematical or calculus operations when we are deriving the expression of the surface with one of the parameters. Simply derive the matrix, simply derive the terms individually inside the matrix which contains the relevant terms with respect to that parameter. So, if we are deriving with respect to U, the first matrix capital U gets derived, and therefore, we will have instead of 1 U, U square, U cube, we are going to have 0, 1, 2 U and 3 U square. That is it. We have found out the expression of the partial derivative of the surface with respect to the U parameter, and it looks like this one. And the last expression gives us the partial derivative of the surface with respect to the W parameter, and it looks like the last row expression which has been provided. So, finding out tangents that way is not a very difficult task. The two specific tangents that we are talking about. One multiple choice question. at the bottom we can see that a vertical plane is intersecting a parametric surface. We will call this a curved surface. Okay, curved surface. A curved surface is being intersected by a vertical plane, and at this point we have drawn the tangent to that particular intersection curve. Now, the MCQ reads, if a vertical plane cuts a curved surface, if a vertical plane cuts a curved surface as shown, the curve of intersection is always a straight line, cannot be a planar curve, has a tangent which is also tangent to the curved surface, and none of the others. Let us take the first option. The first option reads, it is always a straight line. That is obviously wrong, it is not correct. Cannot be a planar curve. Planar curve means that a curve which can ultimately be put into a plane, contained in a plane. But it seems that it will always be a planar curve, because it is essentially going to belong to the plane and essentially going to belong to the surface. So, if it belongs to the plane, it must be planar. So, obviously, this is also wrong. Has a tangent which is also tangent to the curved surface. Since the curve is belonging to the surface, that means is a subset, all the points on the curve, they are belonging to a set of points belonging to the surface, it is a subset. Therefore, the tangent to the curve will essentially be a tangent to the surface. So, this is correct. The third one is correct. Coming back to the surface calculations. So, if we are given the problem of finding out the tangents to the surface with respect to the parameter values parameters u and w, we can easily find it out. Next, and also we know that the cross product of these two tangents will also give me the normal. Now, we are talking about a curve which is lying on the surface. So, just think of it, there is a surface which is say r u w, and on that there is a curve which is lying, which we are referring to as r, a function of a parameter t. So, we are bringing in a third parameter t. But is this something which is faced in the real world? That is this a problem really, or is something abstract of no importance? This will definitely be a problem when we are finding out cutter paths which are moving along curves on a parametric surface. That time we will definitely face this particular problem. Now, if we are dealing with such a curve, how would its tangent be appearing to us? So, in this case we have to essentially find out the derivative of this particular curve with respect to a parameter t. Therefore, first of all we understand that r dash t is equal to dr dt, but r is a function of u and w, r is a function of u and w. Therefore, we can definitely apply the chain rule. So, that we will have del r del u into du dt plus del r del w into dw dt. So, this is the full form of the derivative of the curve r t lying on the surface r u w. Okay. So, del r del u at a particular point on the surface is an invariant, that is it does not depend upon the direction. Whether we are considering a curve in this direction or that direction, it is unique to a particular point on the surface. And further, therefore, these two terms del r del w and del r del u, these points are not depending upon the direction in which we are considering this particular tangent, but dw dt and du dt and dw dt, they are concerned with the direction. They are basically the sort of x and y components of this particular tangent. Okay. So, we understand that this particular tangent expression can also be drawn. Now, we will quickly go through, before ending this particular discussion, we will quickly go through some expressions which will be useful to us in the later calculations. Let us have a look. For example, we are defining L as the second derivative of the surface with respect to u, second derivative dot producted with the normal. So, dot producted with the normal vector. We are defining M as the mixed derivative of the surface with respect to u and then with respect to w, and dot producting with the normal. So, this way we are having these three derivatives involving double derivatives, and the first derivatives are also multiplied, like r dot ru, that means the derivative of the surface with respect to u dot producted with itself made equal to a term called E, f ru dot rw and g rw dot rw. These are required for finding out the curvature of the surface. The curvature of the surface has this formidable expression. We will not be using this much, but this one and this first fundamental form, these will be appearing on and off in our later formulations. These are not very difficult, and I will try to avoid as much as possible mathematical number crunching, and instead we will try to concentrate upon the concepts. Thank you very much.